Hi everyone. So in this video we continue our discussion of conjugate gradients, right? So we agreed last time that the property that we are looking for is not really that D1 should be orthogonal to D2, but that HD1 should be orthogonal to D2, right? And the reason, D2 is basically, to recap, the direction that we take, the direction that the line search works on in the second iteration. D1 is the direction that the line search works on in the first iteration. So in general, HDT, right, should be orthogonal to DT plus 1. So the dot product between them should be 0, right? And the reason is very simple, is that you don't want to undo the progress that you have done while finding the minimum cost along dt, while you are searching for the minimum cost along dt plus 1. And to do that, you don't want the gradient, because the minimum cost is defined by the critical point where the gradient is 0. You don't want the gradient of the cost along dt, sorry. You don't want that to change while you are searching along dt plus 1. And what defines the change of the gradient is the Hessian. What defines the change of the gradient along dt is basically the projection of the Hessian along dt, right? So you want that to be 0, right? If you have this, then d1 and d2 are conjugate gradients, and you get the guarantee, which is basically, if the function is quadratic, then k iterations, where k is the dimension of the parameter space, would be sufficient for finding the optimal solution, right? So let's see what this method does in terms of the problems or the challenges with Newton's method that we discussed when presenting Newton's method. So when presenting Newton's method, we mentioned that there are two challenges, one from an optimization perspective and one from a computational perspective. The optimization perspective problem is basically related to the abundance of saddle points in a large parameter space, because Newton's method jumps directly to a critical point, and because we have a large parameter space, so it's more likely that this critical point will have a mix, the Hessian will have a mix of positive and negative eigenvalues, or that this critical point would correspond to a mix of maxima and minima along the different directions, and that's the saddle point issue. So these are undesirable points. Now what conjugate gradients does is that instead of doing the search or the jumping to the critical point in a large parameter space, it splits it into parameter spaces that are single dimensional, right? Because every line search is a search in a one-dimensional parameter space, right? Then I can fine-tune that line search algorithm, right? So remember, we didn't specify when using conjugate gradients what's the line search algorithm. So you really can use any algorithm that would guarantee that you find a minimum rather than a maximum in the single dimensional space, and that becomes a much simpler problem because this is just a one-dimensional space. Right? So from the optimization perspective, we can avoid the saddle point. So we can solve this problem. There remains the problem of the computation of the Hessian. Because the computation of the new direction, dt plus 1, involves some kind of an inverse of the Hessian, right? So I have to know the Hessian, and I have to be able to guarantee that this condition holds, right? So basically I have to know the direction orthogonal to HD1, right? So this computation of the Hessian can be excessive, right? Or to know the information about the null space of the Hessian, or what direction would be orthogonal to HD1. So what usually happens is that we typically rely on approximations. I'll just mention these approximations without proof. The proof would be out of the scope of this lecture, but I can tell you an insight to make sense out of them. So basically the approximation is the following. You choose dt, the new line search direction corresponding to iteration t, to be the gradient, right? So this is the same as steepest descent. And then the new part to guarantee the dt minus 1 equals 0, or to approximate that, you basically add a component that depends on dt minus 1, right? And with a coefficient beta t here, right? So you have this component, and then you don't compute h at all. And there are two typical approaches to do that. One is called Fletcher-Reeves, and one is called Polak-Ribiere. And they correspond basically to the authors that introduced them. And if you look at the expressions for both Fletcher-Reeves and Polak-Ribiere, you would find that beta t is basically corresponds to what looks like a normalizing factor. And so for Fletcher-Reeves, for example, you have the norm of the gradient of the new gradient divided by the norm of the old gradient, right? So theta t, the point that I stop at after t minus 1, after the line search in iteration t minus 1, the starting point for iteration t. So this is the new direction dt, the new direction that would have been the new direction with steepest descent. And this is the old gradient, right? Which basically that would have been the old direction if I'm using that would have been dt minus 1 if I'm using steepest descent. So basically I'm normal. So if the new gradient has a much larger norm, then beta t is large. If the new gradient has a much smaller norm corresponding to the old gradient, then beta t is small. Okay? And basically the intuition here is that you want to add a factor along the old direction that is proportional, right, to the difference in magnitude, right, or the ratio of magnitudes between the new direction and the old direction, right? So that you have, like, you can think of them as balancing factors between the new direction and the old direction, right? Because all you care about is the direction, not the magnitude, right? So if this gradient with respect to theta t has a much larger magnitude than the one with respect to theta t minus 1, then I add a large factor times the old direction, right? So that they make up times the old gradient, right? So remember that this is not exact, because dt minus 1 is not exactly the gradient at theta t minus 1, because dt minus 1 also has a factor that's a function of dt minus 2, right? For Polak-Ribiere it's similar, but instead of the norm of the new gradient, you take the difference of the new gradient minus the old gradient and you project it along the new gradient, okay? And you also divide by the norm of the old gradient. So the idea is the same intuition holds. If the norm of the new gradient is much larger, then this coefficient is large. If the norm of the new gradient is much smaller, then this coefficient is small. Now there is a theoretical proof that if the function is quadratic, you have the same guarantee as conjugate gradients, meaning that this method, even without computing the Hessian, would also converge in k iterations where k is the dimension of the parameter space. So it guarantees that the new direction defined here by the gradient plus this coefficient times dt minus 1 for both methods is guaranteed if the function is quadratic to be conjugate to the old direction. Thank you.